This is the first video in the stoichiometry unit, just titled Basic Stoichiometry. And you can see we have two learning targets here. We want to be able to identify mole ratios in balanced equations. And we want to perform basic stoichiometry calculations, what I will call gram, mole, mole, gram problems, and you'll see why that is in a little bit, and combinations thereof. As always, you got a good list of resources here. I'd encourage you to check those out. Alright, so the key ideas. First of all, just the word stoichiometry. I think it can be a little intimidating at first. It looks kind of hard, but when we just break down the word, I think it helps us to understand what it is that we're doing. Anytime you see this root meter and with a Y on it, in this case obviously pronounced metry at the end, what this is telling you is that we're studying measurement. Okay, so this is studying measurement. And the question is, what are we measuring? Well, this root here at the beginning, I do not recall what word it comes from. It comes from the German language, I'm pretty sure. But it means amounts or quantities. So when we see the term stoichiometry, what it is we are studying, it is the study of measurements of amounts in chemical reactions. So it just deals with how much reactant, how much product, and those relationships. That's all it is. That's all stoichiometry is. Question might be, if you have X number of grams of this reactant, how many grams of product will you get? Something along those lines. That is what it is that we'll be studying with stoichiometry. If we look at the first learning target here, it says we need to be able to identify mole ratios in balanced equations. That really is the entire whole of stoichiometry. So I'm just going to give you an example of what we mean by that. Let's say we had this reaction. Let's say we had, this is a reaction we've seen quite a bit. Let's say we had copper solid reacting with nitric acid. You need a 4 coefficient there to balance that. And our products here, we get copper 2 nitrate, CuNO3 and that will be aqueous. We get water, and that will be liquid. You'll need a 2 coefficient in front of that to balance it. And we would also need a 2 in front of the is it NO2? Yeah, NO2 is the other product, and that is a gas. We've learned to balance equations, and in that we've said what these coefficients tell us is the number of particles. So for example, if we just look at the reactants here, 1 atom of copper, when it reacts, will react with 4 molecules of nitric acid. That's what those coefficients tell us. But it also tells us a number of moles, a mole ratio, because as we know, if we have 1 mole of anything, whether it's copper or nitric acid or water, we have Avogadro's number of those particles. So if I have 1 mole of copper, that would be 6 times 10 to the 23rd atoms of copper. If I had 1 mole of nitric acid, it would be 6 times 10 to the 23rd molecules of nitric acid. But I can just turn these numbers here, these coefficients, just underlining the coefficients. And remember, if there is no coefficient in front, like we have in front of the copper and the copper 2 nitrate, it's understood to be 1. Those are mole ratios. So if I look at this, what this tells us is that 1 mole of copper reacts for every 4 moles of nitric acid. And I could say that about any of these reactants or products. I could just as easily have written 1 mole of copper reacts to form 2 moles of water. That's what those coefficients tell us. We can use these as conversion factors. So remember, a conversion factor can be written with either of the values in the numerator because it's a fraction equal to 1. So I know that 1 mole of copper over 4 moles of nitric acid would be the same value as writing 4 moles of nitric acid over 1 mole of copper. That would be the same value. So I can use that as a conversion factor. This is the only new idea that we're going to see in this entire video. Everything else is just using what we've already learned in combination with this, and we'll be able to do these problems. So, jumping to the example problems. We are told, consider the reaction between hydrogen and oxygen to form water. Notice we're given an equation. Notice it has already been balanced for you. You must always have a balanced reaction in a balanced equation in order to do these problems, because as we saw up here, these coefficients give us the mole ratios that we're going to need. Alright, so looking at the problem, we are asked if 2.50 grams of water are produced, what mass of oxygen reacted? So this is just some dimensional analysis. The units of my answer are going to be grams of oxygen, grams of O2. Notice it's O2, it's diatomic. And I want to know what mass reacted to get 2.50 grams of water. So that's where I will start the problem. Every stoichiometry problem uses the mole ratios in the balanced equations. If I can go back up here and underline those. We have 2 moles of hydrogen, 1 mole of oxygen, and 2 moles of water. So that tells us what I'm going to use in this problem. I'm relating water and carbon dioxide. Not carbon dioxide and oxygen. I can see that we get 2 moles of water for every 1 mole of O2. Now I could write it like this, or I could write it the other way around, and we will figure out which way we're going to need to use it here in just a second. Before we use one of these conversion factors, though, we have to convert our grams into moles, because grams does not cancel with either of these conversion factors. So we need to use the molar mass of water. Well, we know, or we can calculate if you don't know this off the top of your head, the molar mass of water is 18.02 grams per mole. So notice grams of water cancel. We now have moles of water. Now we can use our conversion factor, this mole ratio that we've written here. Ask yourself which conversion factor, the first one or the second one, would we want to use. If you answered the second one, that would be correct. And we know it's the second one because we can see moles of water cancels if I put it in the denominator. So 2 moles of water in the denominator will cancel with the moles of water from the previous conversion factor, and 1 mole of oxygen on top. Now if I stopped here, the units of our answer would be moles of O2. However, that's not what we want. We want to find mass, grams of O2. So we need to use the molar mass to convert back from moles to grams. Notice it is O2. If you look at the periodic table and you see 16 for oxygen and just use that as the molar mass, that would not be correct here, because we have 2 moles of oxygen atoms in every mole of oxygen gas. So that's 32.00 grams of O2 for every mole of O2. And notice our units cancel to give us grams. So at this point, we just need to calculate our answer here. So 2.5 divided by 18.02 divided by 2 times 32. You will get 3 sig figs here. This initial mass has to be measured. So I get 2.22 grams of O2 is why I end up getting there. A note about the sig figs here. The mole ratios, those are not measured. They are exact. Recall that we said that these come from the balanced equation, which relates particles. So if we look at the balanced equation here for oxygen and water, 1 molecule of oxygen reacts to give 2 molecules of water. You can't have part of a molecule. It's not 1.08 molecules of oxygen. It's exactly 1. So that's why these are exact. So those will never limit your sig figs, those mole ratio conversion factors. One other point to make here, actually a couple other points when I think about it. First point, a common error that I will see is if you look at the molar mass of water here, that conversion factor, what I will see a lot of students do is I will see a lot of students try to put in the coefficient 2, because there's 2 in front of the water in the balance equation. They'll try to put the number 2 here in front of moles of water because they see the 2 there. That is not correct. As we learned, when we calculate molar mass, that is always the mass of 1 mole of water. So to emphasize that, I'll go ahead and write the number 1 here. Same thing over here for the O2. That is the mass of 1 mole of O2. The only time we use the coefficients from the equation is here in the mole ratio conversion factor. I'll just make a point of that here. This is from the balanced equation. Okay, so that's an important point to be made there. The other point that I'd like to make here, and this just applies to all the problems, I like to call these types of problems gram, mole, gram problems. And the reason why is pretty clear if you look at the numerators on all these units here. You can see that we start with grams of water, and we convert that to moles of water, which we convert to moles of oxygen, which we convert to grams of oxygen. So grams, moles, grams. Almost all the problems, and in this video, all the problems, and most of the problems in this whole unit, will be this problem or some combination within it. We won't always have to do the whole thing, grams to moles to grams. Sometimes we'll be able to start with moles or end with moles, depending on what we're being asked. But it's always going to be some combination of this, at least for the great majority of these problems. So let's keep that in mind, and let's take a look at the next question. We are asked to consider the reaction between aluminum chloride and sodium hydroxide, and you can see we're given an equation here. And we're asked what mass of aluminum hydroxide can be produced if 2.87 grams of sodium hydroxide react with excess sodium. Ooh, that is written terribly. I just realized this. Let's see. It should say what mass of aluminum hydroxide can be produced if 2.87 grams of sodium hydroxide react with excess, should be aluminum chloride. That's what this should say. Just caught that here. That should say aluminum chloride. First thing I notice, and we should always look at this before we do any of these problems, this equation is not balanced. We always have to have a balanced equation. Always. Even though it doesn't tell us to balance it, we have to check to make sure that it is. So, to balance this equation, we are going to need, I'll just rewrite it down here. Let's see, it would be AlCl3 plus we would need 3 moles or 3 particles of sodium hydroxide, and that gives aluminum hydroxide, and we would need 3 moles of sodium chloride. That's what we would need there. So we can see 1, 3, 1, 3 on our balancing. So going back to the question, we're asked to find what mass of aluminum hydroxide. So the units of my answer are going to be grams of AlOH3 are equal to, it says what mass of aluminum hydroxide can be produced if 2.87 grams of sodium hydroxide, so that's where I'm going to start, 2.87 grams of sodium hydroxide, and it says that sodium hydroxide is reacting with excess aluminum chloride. What that means is we just have plenty of aluminum chloride to make sure that all of this sodium hydroxide will react. So we know all 0.287 grams will end up being consumed to form products. So looking at the problem here, we're starting with grams, a mass of sodium hydroxide. We need to find mass, grams of aluminum hydroxide. This is the exact same format as we just saw up here. This is a gram, mole, gram problem. So the first thing I need to do is I need to convert to moles of sodium hydroxide. I need the molar mass to do that. So we'll calculate the molar mass of sodium hydroxide. Sodium is 22.99 plus 16.00 for oxygen plus 1.01 for hydrogen. That tells you 40. So because all those go to 2 decimal places, I'll write 40.00 grams of sodium hydroxide for every mole of sodium hydroxide. Grams cancel. Now we need to use the mole ratio. So we can go from moles of sodium hydroxide to moles of aluminum hydroxide. That comes from the balanced equation. We can see here 3 moles of sodium hydroxide react. We get 1 mole of aluminum hydroxide. So that is the mole ratio. 3 moles of sodium hydroxide would go on bottom. 1 mole of aluminum hydroxide goes on top. Moles cancel. And we now have moles of aluminum hydroxide. Finally, we need to go from moles into grams. So we need the molar mass of aluminum hydroxide. So aluminum is 26.98 plus 3 times 16 for oxygen plus 3 times 1.01 for hydrogen. And that gives us 78.01 grams aluminum hydroxide for every mole of aluminum hydroxide. And moles of aluminum hydroxide cancel. Now it's just a matter of plugging in all the numbers to get our answer. We have 0.287 divided by 40 divided by 3 times 78.01. We get 3 sig figs here, the 0.287. Oh, sorry, you guys couldn't see the calculator there. So with the 3 sig figs, that would be 0.187 grams aluminum hydroxide. There's our answer. Okay, there is one more example problem. It says, determine the number of moles of sodium chloride that can be produced from 15.5 grams of chlorine gas when it is reacted with excess sodium. Notice we do not have an equation here, so we have to write the equation. So we can tell sodium chloride is the product because we're asked to find the number of moles of that can be produced from chlorine gas and sodium. So my reactants would be Cl2 and Na, and that's going to give us sodium chloride, NaCl. We need to balance the equation, and it looks like we would need 2 moles of sodium chloride to balance the chlorines, which means we would need 2 moles of sodium. And we are asked to find the number of moles of sodium chloride, question mark, how many moles NaCl are going to be formed if we react 15.5 grams of Cl2. Remember, chlorine's diatomic, that's all you know, that's Cl2. So notice in this problem, this is not the full gram, mole, gram, because we're asked to find moles of sodium chloride. So this is going to be a gram, mole, is all this is going to be. So I need to convert grams of chlorine into moles of chlorine. So we need to find the molar mass. So that is 35.45 times 2. So that is 70.90 grams Cl2 for every mole of Cl2. And then now we need to go from moles of Cl2 to moles of NaCl. That's here in our balanced chemical equation. From the equation I can see we get 1 mole of chlorine reacting for every 2 moles of NaCl that are produced. Moles of Cl2 cancel, and that is all the problem is. So we have 15.5 divided by 70.90 times 2. That is 0.437 moles NaCl. So to summarize, every stoichiometry problem uses a mole ratio coming from the balanced chemical equation. If we need a mass or we are given a mass, then we would need to use a molar mass to convert it to moles or to convert from moles to grams at the end if we need to find a mass. That is stoichiometry. Alright, I would pause the video here, try out the practice problems, and then see how you did. Alright, so it says, write the equation for the reaction between magnesium and hydrochloric acid, producing magnesium chloride and hydrogen. So magnesium would just be Mg. Hydrochloric acid that contains hydrogen and chlorine, that would be HCl, because hydrogen is 1+, chlorine's or chloride's 1-. And then we get magnesium chloride. Oh, that should be an arrow, not a plus sign. So magnesium chloride is MgCl2. And hydrogen, that is H2 because it's diatomic. So to balance, we would need 2 moles of HCl, and that should be it. A. What mass of hydrochloric acid is required to completely react with 1.2 grams of magnesium? So we need to find a mass of HCl, and we want to know what mass is required to react with 1.2 grams of magnesium. So that's where we will start. So this will be a gram, mole, mole, gram problem. We're starting with grams, we're ending with grams. So we need to convert from grams to moles for magnesium. The molar mass of magnesium is 24.31 grams of magnesium for every mole. Magnesium. Grams cancel. Now is where we need the mole to mole ratio from the equation. We look at our balanced equation, we see we have 1 mole of magnesium and we have 2 moles of hydrochloric acid. Now we just need to convert from moles to grams for hydrochloric acid, so we need the molar mass. That is 1.01 plus 35.45. That gives us 36.46 grams HCl for every mole of HCl. Moles cancel. And we just need to find our answer now. So we have 1.2 divided by 24.31 times 2 times 36.46. And that gives us 2 sig figs, 3.6. 3.6 grams HCl. Question B. What mass of magnesium chloride, so we're looking for grams, how many grams of MgCl2 can be produced if 0.25 moles of hydrochloric acid react? 0.25 moles HCl. So notice this is not a gram, mole, mole, gram. We're starting with moles. This is the first time we've seen this. In all of the problems we've done before, we always used a molar mass as the first conversion factor. That was always because we had a mass to start with. We had to convert from grams to moles. We're already starting with moles here, so we don't need a molar mass to start with. If you did use the molar mass of hydrochloric acid here to convert to grams, you would be going backwards. Okay, it would be like you're starting here with moles. Obviously, this is magnesium, not hydrochloric acid, and you'd be going back to grams. We don't need to do that. So the first thing we can do here is we can just use our mole ratio to go from moles of HCl. I can see that we have 2 moles of HCl that react, and we get 1 mole of magnesium chloride. Moles cancel, and we have moles of HCl cancel. We have moles of MgCl2. Now we just need a molar mass. So calculate that. Magnesium is 24.31 plus 2 times 35.45. That gives us 95.21. 95.21 grams MgCl2 for every mole. MgCl2, moles cancel, and we have done the problem. So just plugging in our values here, 0.25 divided by 2 times 95.21. That is, let's see, we get 2 sig figs, so 12 grams MgCl2. Last question. How many moles of hydrogen are produced if 0.50 moles of magnesium react? So we're looking for moles. How many moles of H2 do we get when 0.50 moles of magnesium react? Well, starting from moles, we're going 2 moles. So this is only a 1 conversion factor problem. We just need to use the mole ratio in the equation. We can see that we have 2 moles of magnesium. Excuse me, not 2 moles, so it's 1. 1 mole of magnesium. 1 mole of magnesium for every 1 mole of hydrogen. And that's it. So if you're converting from moles to moles, it's just using the mole ratio. And in this case, because it's a 1-to-1 ratio, that will just give us 0.50 moles of H2. And that's it.